All right. Good evening, everyone. Um, so I'm just going to go ahead and run through this last exam here. The series exam is always the hardest. It's always the one people struggle with the most. And I just wanted to go through it and be really thorough about how I'd like these things done. So let's just jump on into it. First question, can you use the test for divergence or divergence test to determine if sum n equals 1 to infinity 1 over n converges or diverges? Well, the test for divergence requires that we take the limit as n approaches infinity of the sum end 1 over n, and naturally that's 0. But the divergence test also says that if that limit is 0, our series is only possibly convergent. We can't guarantee that it is convergent. All we can say is that it may converge. Okay. So this doesn't give us an answer either way. It doesn't tell us that this series diverges. It says it may converge, but it doesn't tell us that it does converge. So we get no information from the divergence test. So no, the divergence test is inconclusive. Okay. Kind of a little easy one to start off there. Okay, can you use integral test to determine if sum n equals 3 to infinity 1 over n converges or diverges? Okay, so we need 3 ingredients really for integral test, right? We have to say, okay, let's let f of x be 1 over x, okay? The first thing we need to check is it positive? Okay, well, on the interval 3 to infinity, so I'll say this, let f of x be this, and then on the interval 3 to infinity, f of x is greater than 0, right? Because we have a ratio, the numerator is positive, and the denominator will be positive in this window. So yeah, we have positivity, check. Okay, next thing, we need it to be decreasing. And we can check the first derivative. That's minus 1 over x squared. And that first derivative, by similar argument, is always negative on 3 to infinity, which tells us that f is decreasing. Okay, and the third ingredient we need is continuity, but we know that f prime, or I'll say it this way, f is differentiable on 3 to infinity, and differentiability implies continuity. So if a function is differentiable, it's guaranteed to be continuous, okay? And it's a rational function, and rational functions are differentiable everywhere where they're defined. So aside from asymptotes, vertical asymptotes, rational functions are all differentiable. So those are our 3 justifications. So it fits the form of an integral, of the integral test. So yes, integral test may apply. Okay. The other simpler way that we could justify that it's decreasing is we can say, look, the numerator is a constant and the denominator it's always positive, so we don't have to worry about some sort of sign oscillation. And it's getting larger. So we have a fixed numerator and a denominator that's growing. That will also be decreasing. So you can think about it two different ways. Just make sure that you don't just say, yeah, it's decreasing. You need to justify these things. I can't be in your head. So you need to tell me, here's why it's decreasing. Okay, it's decreasing because this, and this, and this. Okay, the most rigorous way to do that is with the first derivative, but I digress. Okay, number 3. Determine if the series sum j equals 1 to infinity arctan of j over 1 plus j squared converges. Okay, there's 2 ways you can do this one, and I think one is honestly easier. A lot of people tried to do the integral test here, and that's fine as long as you justify it. A lot of people also used a mix of direct comparison and integral, and there was no need for the mix. You can either use direct comparison or integral test, and we'll get what we want. But with integral test, we have to show 3 things, right? Continuity, positivity, and decreasing. But direct comparison, it's pretty easy. So I'm going to say, let's apply direct comparison. Okay. So I'm going to start with sum j equals 1 to infinity of 1 over j squared. And we know this is convergent by p-test, right? So since it's convergent, we know that if we multiply by pi over 2, and I'm kind of working backwards, and sometimes with direct comparison, you kind of have to work backwards this way. But we know that this will also be convergent, right? Because if this sum is convergent, it's just a finite number. So we can go ahead and multiply a finite number by pi over 2, which is also finite, and that's not going to affect the convergence at all. And since it's convergent, we can distribute. So we have that the sum j equals 1 to infinity of pi over 2 over j squared is convergent. Okay. Now we need to be careful and prove some inequalities. Okay. So we have arctan of j over 1 plus j squared is less than or equal to arctan of j over j squared, right? And just reasoning through this, well, the numerators are the same, so it's up to the denominators. Well, this is positive, and whenever we add 1 to a positive number, it's always larger than what we started with. So we have a larger denominator on the left-hand side there, and on the right-hand side, we have a smaller denominator, which makes the whole thing, the whole ratio, larger. Okay, but we need to take this just a step further and remember that arctan is bounded above by pi over 2. So the first step was kind of bounding the denominator, and the second step is bounding the numerator. So this is bounded above by pi over 2 over j squared. Okay. So we have that this summand, I'll switch colors here. This summand is greater than or equal to this summand for all j in natural numbers, or 1, 2, 3, dot, dot, dot. Therefore, since sum pi over 2 over j squared, j is 1 to infinity, converges, then by direct comparison, we have that the sum j equals 1 to infinity arctan of j over 1 plus j squared converges. And the way I think about these things is this kind of looks like a 1 over j squared p-test kind of thing. You just need to kind of reverse engineer and say, okay, well, the numerator, I can bound that by something, and the denominator's even larger. So, you know, you just kind of work the pieces backwards and say, okay, I'm going to start with 1 over j squared. Okay, you know, can I bound this, and then can I bound this? It's a little bit trickier to use in terms of like, I guess like the fundamental understanding of what's going on and how to use these inequalities. But in the implementation, it actually is just quite a bit easier than in an integral test, because then you have to do a u sub, and I don't want to do that. Okay. 4. Oof. Determine if the series k equals 5 to infinity 3 over k minus 2 k plus 1 converges, and if it does, find its value. Okay, so the key tip off with these is that we're telling you to find its value. Realistically, under or outside of very specific circumstances, actually finding the sum is not easy. When we tell you to find the value of the sum, 2 things should pop into your head. It's either telescoping or geometric. And this is not a geometric form. So this tells me that we're going to be dealing with a telescoping, okay? So as we've done before, we want to use a partial fraction decomposition to more easily see the telescoping behavior of this sum. Okay, so we get that 3 is a k plus 1 plus b k plus 2. 3 is a k plus a plus bk plus 2b. And then we'll group like terms. So we have 3 is a plus b times k plus a plus 2b. So we get 2 equations from this information. We know that a plus b has to be 0 because there's no k's on the left-hand side. And we know that a plus 2b has to be equal to 3. So this tells us that a is minus b, and we can go ahead and substitute that into this equation. Minus b, I think I have a sign error here. Yep. Should be k minus 2. Minus 2b minus 2b minus 2b. Okay, so that's minus b minus 2b is equal to 3, or minus 3b is 3, which tells us that b is minus 1, and plugging that back into this equation, we infer that a is 1, okay? So our partial fraction decomposition works out to being 3 over k minus 2 k plus 1 is equal to 1 over k minus 2 minus 1 over k plus 1. Okay, I'll erase this. Okay, so now we can start writing out some terms. And I'm just to stay consistent with the notation, I'm just going to index this at 5 technically this is the first partial sum because it's not defined for k less than 5, but again, just to make it absolutely clear, I want to be pretty careful with that. Okay, so S5 is 1 over 5 minus 2 is 1/3 minus 1 over 5 plus 1 is 1/6. S6 is, well, it's 1/3 minus 1/6, and then plus 1 over 6 minus 2 is 4, minus 1 over 6 plus 1 is 7. S7, 1/3 minus 1/6 plus 1/4 minus 1/7 plus 1 over 7 minus 2 is 5, minus 1 over 7 plus 1 is 8. Okay, and then when we plug in 8, we get plus 1 over 6 minus 1 over, excuse me, I had to sneeze. 1 over 6 minus 1 over 8 plus 1 is 9, okay? And here's where we observe the first cancellation. Those go away, okay? And just to be super redundant, I'll write out S9. Minus 1 over 9. And then that's plus 1 over 7. 1 over 9 minus 2 minus 1 over 9 plus 1 is 10, okay? And then we get a cancellation, okay? So starting at 6, and then it goes to 7, and then it goes to 8, every fraction with a denominator larger than 6 is going to eventually get wiped out, okay? So in general, I'll erase some of these. So in general, the nth term, I guess I'll use k. The kth term of this sequence of partial sums is 1/3 plus 1/4 plus 1/5, and then it's minus, and we use the subscript here to kind of guide us along. So this is minus 1 over k minus 1, because if k was 9, that's k minus 1 right here. And then we have minus 1 over k plus 1. Plus where was I? Oops, sorry. Okay, so that's 1 over k minus 1, so that should be k, excuse me. And then it's 1 over k minus 2. Let me just make sure I have that right. So we have k minus 1, we have k, and we have k plus 1 because I canceled out the 7, right? Okay, now it makes sense. Now, to find the value, we take the limit of the sequence of partial sums, right? So we want, well, the limit as k goes to infinity of sk, which is limit k goes to infinity 1/3 plus 1/4 plus 1/5 minus 1 over k minus 1 minus 1 over k plus 1 over k plus 1, right? But limits distribute over sums, so this is 1/3 plus 1/4 plus 1/5 plus the limit as k approaches infinity of minus 1 over k minus 1 minus 1 over k plus 1 over k plus 1, because constants are unaffected by a limit. These guys don't care about what k does, so the limit is just the constant, right? So evaluating this limit, well, this goes to 0, this goes to 0, this goes to 0. So our limit of partial sums is just 1/3 plus 1/4 plus 1/5. And then if we wanted to get that over a common denominator, we would multiply the first fraction top and bottom by 20. So that'd be 20 over 60. We would multiply the second fraction top and bottom by 15. So that's 20 plus 15 over 60. And then we will multiply the third fraction top and bottom by 12. So that's 60 and 12. And then adding that all together, we get 20 plus 15. That should be 47 over 60. And that, recall, is the value of the sum, because it's the limit of the partial, the limit of the sequence of partial sums. Okay? So since that number is finite, we conclude that it converges, and it converges to 47 over 60. Okay. Oh, sorry, I seem to have lost my notes for number 5 here. Let me just pull that up then. Oh, I missed one. Oh, that's the problem. Okay. So that should have been the partial fractions. That should have been number 5. Number 4 says, suppose p to the n is non-zero for all n, and the sum of p to the n equals 1 to infinity converges. Can you say for sure if sum 1 over p to the n from 1 to infinity converges or diverges? Okay, a lot of people had trouble with this one, and to be totally honest, it was the simplest problem on the exam. You have to know certain properties about convergent sums. Convergent sums have the property that if Pn converges, that implies we are guaranteed that this happens with a convergent sum, that the limit as n goes to infinity of p to the n is 0. Okay? Well, if that limit is 0, then we know that the limit as n goes to infinity of 1 over p to the n is limit n goes to infinity of 1 over limit n goes to infinity of p sub n. The denominator, the numerator is fixed. The denominator is wanting to go to 0, right? Which tells us that this wants to go to infinity. Now, there's some nuance here with, like, does it want to go to positive infinity or negative infinity? But that doesn't matter, because we know that the limit is not 0. That's the key. So not 0. And if it's not 0, then by divergence test, that sum has to diverge. So we can conclude that 1 over p to the n diverges by divergence test. Okie doke. Suppose a is a real number, and we want to determine for which values of a the series k equals 1 to infinity 4 minus 2a over 1 plus a squared to the k converges. Okay? It's important to see here that we asked you, like, it converges for some values. That should be a little tip off to you that it converges, like it's not always diverging. Okay, so if you ran through a test and you got that it always diverges, you know, you probably didn't do something right. So, you know, just think, what kind of form is this, right? And it's the form of a geometric series. So we're going to apply what we know about geometric series. We know that geometric series only converge when what's being raised to the kth power is strictly less than 1 in absolute value. So that's 4 minus 2a over 1 plus a squared in absolute value is less than 1, okay? But we don't like that absolute value being there, right? Because it makes algebra hard. So we can go ahead and open this up in such a way where it's -1 is less than 4 minus 2a over 1 plus a squared. Okay, and then we just have these compound inequalities to solve. And that's not so bad. So I'm going to multiply all three by 1 plus a squared. Okay, and I can do that without changing the signs because 1 is positive and then I add a squared, which for all real numbers is either positive or 0. But in either case, the whole denominator is positive. So that tells us that -1 minus a squared is less than 4 minus 2a is less than 1 plus a squared, okay? Now, I'm going to break this down into two pieces, this inequality and this inequality. I'll color code this, okay? So, first inequality, -1 minus a squared less than 4 minus 2a. Let's get everything over on one side. So we have that 0 is 4 minus 2a plus 1 plus a squared. And just combining like terms, that's 5 minus 2a plus a squared. Okay? Now, try as you like. You're not going to factor this one. So it's important to think about some algebra that you may have forgotten. But if you'll recall, the discriminant of the quadratic formula, b squared minus 4ac, okay? B is -2 squared minus 4 times 1 times 5. That's 4 minus 20, and that is less than 0, okay? When the discriminant is negative, you have no zeros of your function, okay? Which means that this parabola doesn't cross the x-axis ever. So it's either always negative or always positive for all values of a, okay? And for the record, if the discriminant is 0, you have one place where it crosses the x-axis. If it's positive, you have two places where it crosses the x-axis. It's a handy little thing to remember. So we know that this is always either positive or negative. Well, let's just take a test value, right? Any one will do. Let's try 1. Well, we have 5 minus 2 plus 1. Yeah, that's positive. So this is always greater than 0 for all a real valued, okay? So that doesn't really restrict us. That particular inequality says, yeah, we can take a to be whatever, okay? But we need to think about the other inequality first. Okay, so we have 4 minus 2a less than 1 plus a squared. And I'm going to do the same thing. I'm going to get everything over on one side. So that's 1 minus 4 plus a squared plus 2a, right? Okay, and then we'll say that that should be greater than 0. Okay, combine like terms. So that's what, -3. And I'll rewrite it in the standard form of quadratic as a squared plus 2a minus 3. So we have 0 is less than a squared plus 2a minus 3. And that factors into a plus 3a minus 1. Okay, so now we have two cases. Either both of these factors are positive or they're both negative. Okay, so we want to know for what values of a this is true, and for what values of a minus 1 is also less than 0. So that's a less than 1 and a less than -3. So we have to take the more restrictive inequality. Okay, so this tells us that we can have -infinity to 1, and this tells us that we can have -infinity to -3. That's the more restrictive one, so we're gonna take that. Okay, and now we have to consider the case where they're both positive. So we have a plus 3, well, don't need the parentheses. We have a plus 3 greater than 0 and a minus 1 greater than 0. That tells us that a has to be greater than 1 and a has to be greater than -3. So this tells us that we have -3 to positive infinity, and this tells us that we have 1 to positive infinity. That's more restrictive, so we're going to take that. Okay, so finally, so the values of a for which the series converges are -infinity to -3 union 1 to infinity. Any value of a in there in our series will converge. Okay, now take a breath. We're almost done, and we need to find the value in terms of a. So just go ahead and erase some of this. Now, since this is a geometric series, we can go ahead and find that value, right? So I'm going to write this as k is 1 to infinity, 4 minus 2a over 1 plus a squared to the k. That's the same thing as k equals 1 to infinity, 4 minus 2a over 1 plus a squared times 4 minus 2a over 1 plus a squared to the k minus 1. Okay, now this looks like the kind of geometric series we can apply the formula to. So that is valued as the same as this goes in the numerator and this gets subtracted from 1 in the denominator. So that's 4 minus 2a over 1 plus a squared over 1 minus 4 minus 2a over 1 plus a squared. And if I get a common denominator in here, in the denominator with this 1, I have 4 minus 2a over 1 plus a squared over 1 plus a squared over 1 plus a squared. And I'll go ahead and write this as one fraction. 1 plus a squared minus 4 plus 2a. But now we can cancel these denominators, and we're left with 4 minus 2a over 1 minus 4 is minus 3. So that's a squared plus 2a minus 3. And that's about as simple as I want to put it. So, okay, let's take a breath. 7a. So determine which of the following sequences are increasing, decreasing, not monotonic. Okay, monotonic means either increasing or decreasing. That's all it means. It's just a fancy way of saying it's either increasing or decreasing. So if we have a sequence that's neither, then it's not monotonic, okay? And then bounded or unbounded, okay? And boundedness is tricky too, because you have to consider, is it bounded from below? Is there a minimum value? And is it bounded from above? Is there a maximum value? If you don't have both, you can't conclude boundedness, okay? So you need to have a lower bound and an upper bound. There's a window to trap these things in, okay? So yeah, an is 2 plus minus 1 to the n over n for n greater than or equal to 1, okay? So right off the bat, if we start plugging in values of n, right, the first value is what? 2 minus 1, so it's 1, and then it's 2 plus a half, so that's 2 and a half. 2 minus a third. So kind of what we're seeing is, you know, if we were to kind of plot these values, if this is y equals 2, we'd have this kind of thing going on where, yeah, it's jumping above and below 2, but it's sandwiching overall closer to 2, okay? And we can verify that with a limit, but, you know, we don't need to actually figure out what the limit is. So the way I think about this one is, okay, whenever it's positive and we're above 2, we're adding something less than 1. So it's bounded above by 3, okay? Honestly, it's bounded above by 2.5, but 3 works, 5 works, 10 works. All of those are upper bounds. We're saying that the sequence does not exceed 3, ever. And similarly, the sequence does not exceed 0. So it's bounded above or bounded below by 0, okay? These bounds don't have to be perfect. They just need to exist, okay? And then because we were seeing that dipping behavior, right? We were saying, okay, doop, 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 doop. From here to here, it would look like it's decreasing, but then it increases and then it decreases. So it's not monotonic. It needs to be consistent throughout. So this one is not monotonic, but it is bounded. And then B was an is arctan of n greater than or equal to 0. Okay. Again, arctan is an increasing function. So the sequence has to be increasing. Okay. And we can verify that with the first derivative. It's 1 over 1 plus x squared. And that's positive for all values of x that are real. So we can verify it with the first derivative that is increasing. You can appeal to the graph of arctan. That's totally fine as well. So that's increasing. And since it's increasing on the window n equals 0 to infinity, we know that arctan can be no smaller than 0. So it's bounded below by 0. And we know that as n gets arbitrarily large, it's also bounded above by pi over 2. Okay, and again, negative pi over 2 works for the lower bound, but you know, it doesn't have to be the absolute tightest bound. It just needs to exist. Okay. Okay, and then finally, number 8. Can we use alternating series test to determine if 1 over log of 3 minus 1 over log of 4 plus 1 over log of 5 minus 1 over log of 6 plus 1 over log of 7, dot, 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 right? Converges? Okay, so I'm going to go ahead and express this as k equals 3 to infinity minus 1 over ln of k. And if I want this to match with my k, I need to, so the first term is odd. So if I put a k there, it's not going to match the sign of what we had. So I'm going to put a k plus 1 and then take a look. So if I plug in k equals 3, I have negative 1 to the k plus 1 is 4. So that should be positive, and it's over ln of 3. Okay, that checks out. All right, so can we apply alternating series test? Well, we need two things. Decreasing and limit, okay? So is it decreasing? If you want to call it b sub n or whatever, as the log of k. Of course it's decreasing, right? Because, you know, we can take a first derivative. Don't really need to do that, but we can say that it's a fixed numerator. The numerator is not getting larger, and the denominator is. It's decreasing. Okay, it's decreasing because the denominator is growing, but the numerator is constant. And then we examine the limit as k approaches infinity of 1 over log of k. Well, of course, that's 0. And those are the two things that we needed. So yes. Yeah, we can use alternating series test on this one. Okay. Okay. All right, last one here. To determine, well, I'm not sure I worded that correctly, but whatever. So we have a piecewise defined sequence. Okay. A lot of you tried to split it up and evaluate it as two sums. Now, that wasn't a bad attempt, but it's not really something we can do. Because then you reindex and, you know, do I have the same amount of infinity of these terms? Because really you would have just quintupled the amount of 2 over n terms if we split it like that. So that's a question that likely doesn't have an answer. So really all I was trying to get you to see with this one is that no, we can't apply the alternating series test to this because it doesn't decrease. Yeah, it decreases for a little while, and then it jumps up, and then it decreases for a little while, and then it jumps up. And again, we need it to stay decreasing in general, which means that a sub n plus 1 is less than a sub n for every possible combination. And whenever we have a jump like that, it breaks that rule. So not decreasing. So no, we can't use that test here. Okay, and then I got some, so that was the first test, and then I got some questions about particular things. So I just wanted to show you all how to work with factorials. So here's an example. Determine the radius of convergence of the series x to the n over n factorial. N is 0 to infinity. Okay, so we go ahead and apply ratio test and examine the limit as n approaches infinity of the absolute value of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. Okay, now n plus 1 factorial is the same thing as n plus 1 times n factorial. Okay? Now, as a side note, you know, it may be the case where you have something like n plus 2 factorial. And that all that is n plus 2 times n plus 1 times n factorial. Okay? You take whatever was in here and you subtract 1 from it. So you start with this, n plus 2, subtract 1 from it, n plus 1, subtract 1 from it, you get n minus 1, n minus 2. These are all the factors, but we compactly write that notation as n factorial. Okay? So just something to keep in mind there. So since we have this, we can just go ahead and cancel the n factorial, and we can cancel x to the n. So that limit is n approaches infinity is x over n plus 1. And using some properties of absolute value here, this is absolute value of x over absolute value of n plus 1, but n is positive, plus 1 is positive, so it's just n plus 1. Now, x doesn't care about n. It's unaffected by n, so we can go ahead and slide that out of the limit because it's constant with respect to the limit. 1 over n plus 1, well, that's 0, right? And for all finite values of x, the absolute value of x times 0 is 0, and that's less than 1, and it has no dependence on x. This happens regardless of whatever x value I put in there. So this happens for all, that's what this symbol means if you don't know, for all x in the real numbers, which tells us that the radius of convergence is infinite. So we have that the interval of convergence IOC is negative infinity to infinity. Okay? Okay, it's kind of a lot. But yeah, just whenever you see factorials, I'm not gonna say it's all the time, but it's generally the way you want to work with those is with a ratio test because it cancels so nicely in the ratio test. Factorial it's not a smooth function. It's not differentiable. You know, you don't want to try and integrate it. How would you even integrate something like that, right? So ratio test would be my first thing to reach for whenever I see a factorial. I'm not going to say it's right in every scenario. I don't know that much. Or like, I can't guarantee that. But generally speaking, it's kind of your first line of defense. All right. Now I got this last question on the quiz here. So we have an error function defined as 2 over square root of pi, 0 to x, e to the minus t squared dt. And the first part was compute the derivative. So erf prime of x, and this is just a straightforward application of the fundamental theorem of calculus part 1. Whenever we differentiate an integral with a variable in the upper bound, we just cancel out the integral and we plug the variable in here. So this is just 2 over square root of pi e to the minus x squared. Done. Okay. And then we want to expand in the Maclaurin series and then integrate. Okay. So we're going to expand the integrand first, and e to the x is n equals 0 to infinity, x to the n over n factorial. So if we just plug in minus t squared or minus x squared for that, we have e to the minus x squared is n equals 0 to infinity minus x squared to the n over n factorial. And that's equal to sum n equals 0 to infinity of minus 1 to the n x to the 2n over n factorial, just using properties of exponents there. Okay? And then, since we already know that this converges for all possible values of x, we did that last problem, we can go ahead and integrate term by term. So this is the same thing as n equals 0 to infinity, minus 1 to the n, x to the 2n over n factorial. That's the same thing as moving the integral into the sum here. Okay, now it's important to realize, and I'll put a dx, yeah, dx. It's important to realize that negative 1 to the n factorial, these are constant in terms of the integral. Okay, because the integral only cares about the x. So that's the same thing as sum n equals 0 to infinity. And what do we do when we integrate? We raise the power by 1 of the rate. We raise the power of x by 1 and then divide by that new power. So that's negative 1 to the n, x to the 2n plus 1 over n factorial times 2n plus 1. Okay? And then we're going to use that to write out the first 4 terms. And we want to make sure that we don't forget this factor here. But we'll write out the first 4 terms as 2 over the square root of pi. And then we can just start plugging in n values. So n equals 0, we get negative 1 to the 0 is positive, 0 factorial is 1, so that contributes nothing. And then x to the 2 times 0 plus 1 is x over 1, so it's just x. And then the sign's going to change on us. So negative 1 to the 1 over 1 factorial, so that just changes the sign. And then we have x cubed over 3. And then you get the idea. We're gonna calculate these. So that is for n equals 2, that's positive. So that's x to the 5th over, so 2 factorial is just 2, and then times 5 should be 10. And then that switches again, x to the 7th over, and I got 42 here. Okay, and then the next two questions, we're just asking you to use this polynomial to estimate a value of the ERF function. And so since we expanded our power series near 0 for small enough values, this will be a sufficiently good approximation. So I don't want to actually go through and put those in because it's not really conducive on this on this iPad, but yeah, you would just plug in the value that they want you to estimate wherever you see an x, and then calculate it, put it in a calculator, and just turn the handle and see what comes out. Okay, so you use that to estimate those two, and then the last thing would be they just want you to find what the remainder is, right? Because that would be your error term, basically. So that's m over n plus 1 factorial x minus a to the n plus 1, where the n plus first derivative evaluated at a, sorry, that should be x, less than or equal to m, right? So a is our center. In our case, it's 0 because there's a Maclaurin series. So we just need to figure out what the 5th derivative of that thing is. It's I did it the hard way, and I think I got minus 8e to the minus x squared times x times 4x to the 4th minus 20x squared plus 15, right? And then we're going to evaluate this at our point of interest. So if they're asking us to approximate, I think it was 0.16, we would just put 0.16 everywhere we see an x, and then we'd take the absolute value of it. And we'd see how large that is, and we can call that our m. Since we only had 4 terms, we would say n is 4, and then this x in this case would be 0.16. So that's how you use this particular theorem. It's pretty calculation heavy, so just watch out for that. And I think that just about covers everything I wanted to go through. So thank you for your patience, hanging in there with me. A reminder that the final is on Saturday. So, if you have any questions, get them in now. Other than that, it's been a pleasure working with you all this semester, and thank you.